Hi, in this video we'll explore skip connections. Skip connections are a very important implementation trick that enable the training of deep models. They improve the performance of the model in a very significant way, and they are one of the most important training tricks in deep learning. We'll see that they're quite easy to implement in PyTorch. So our learning goals are to understand the vanishing gradient problem that we solve with skip connections as a numerical problem, and we're going to see how we implement skip connections as either element-wise addition or concatenation of activation maps. Let's start discussing the problem. The vanishing gradient problem occurs during neural network training through backpropagation. Let's explain three key elements in this slide. We have the weight update equation that shows how we adjust the weights. The gradient term is circled in red. Remember that this is the loss with respect to the weights, the derivative of the loss with respect to the weights. This is something that has a very strong signal in the output layers of a model, but a significantly weaker and smaller signal as we move backward through layers. The graph demonstrates this problem in BGG19, a very famous classification model. Notice that the gradient magnitude drops to nearly 90% from the output layer to the input layer, meaning that we're losing most of the gradient signal when we arrive at the input layers. The BGG19 architecture shows why this happens. Each layer in the deep network compounds the problem, making gradients progressively smaller as they flow backward. This is going to cause some numerical instability issues that prevent the deep networks from learning effectively. And the architectural solution that we have found that solves this problem most straightforward is a skip connection. Here we see a more concrete example that we can implement in code to see how is this happening with convolutions. If we create an 8x8 matrix full of ones, and then we create a 3x3 convolution kernel that has values that add up to 0.8, each convolution operation is going to reduce the magnitude of values that comes as output. If we apply this convolution 1,000 times, each iteration is going to multiply the values by less than 1, making them progressively smaller. The code is checking when all of the values have become 0 due to the computer's inability to represent extremely small numbers. This mirrors the vanishing gradient problem in deep networks. And the VG architecture on the right reminds us of a situation where this might happen in a real network through repeated application of convolution operations. This slide focuses on the core issue of numerical underflow, how we have trouble representing very small numbers in computers due to the fact that we have a predefined amount of bits that we use to represent them. If we have a very tiny number, 10 to the power of minus 8, and then we try to square it so that it becomes 10 to the power of minus 16, this is something that we're going to be able to represent with 32 bits, but we're not going to be able to represent with 16 bits. When we do this conversion, you see that the operation, when we apply it on the floating point 16, is simply not enough, like it underflows. The value goes straight to 0. Whereas when we use 32 bits, there's still some numerical result that is close to the correct output of 10 to the power of minus 16. There is a very useful website for the IEEE 754 standard that shows us how computers store these floating point numbers using the bits that we have allocated for them. Note that there are some errors introduced during the conversion. And you see that this is something that is very tightly coupled with the limitations that we have when we're trying to represent small values. We have a fundamental limitation in computer arithmetic that explains to us why gradients might vanish when we have very deep networks. So Resnet introduced skip connections, and this is an architecture that made this trick famous. It was not originally proposed in the Resnet paper, but it's something that was popularized by it. We see here that what we're doing is just an element-wise addition between some original input and the output of some convolutional layers. And what this path that we are creating allows us is to checkpoint the information that we have learned so far. So we have a main route, like the main convolutions that we are applying, and then we have an additional path. Through this additional path, we're creating a direct path for the gradient flow in case that we destroy some information due to numerical underflow in the convolutional layers. This allows us to preserve features from the early layers and allows the network to learn some residual functions, like this path that we're creating as an extra way to access the information that we had before. So this is something that has a very significant effect during training and has been explored in several papers. In this one we see how adding skip connections has a very significant effect on the loss landscape. When we plot the cross-entropy loss that we would get while using the skip connection versus not using the skip connection on a Resnet, we see that the landscape is way more rugged and way more difficult to find an optimal path to the minimum than when we use the skip connection. This smoothing effect that we see with the skip connection explains why these networks train better. And it's curious to note that even though the technique was popularized on the Resnet paper, other models like LSTMs and HighwayNet already used it. It was the big jump of performance that Resnet achieved on the ImageNet benchmark for image classification what made this trick famous, as this is what really allowed us to create very deep models. The model that started the deep learning hype in 2012, AlexNet, had only 8 hidden layers. The VGG model that we saw before, that was also one of the top performing models on the ImageNet challenge, had 19 layers. You see on the graph that in 2014, the deepest model that won the ImageNet challenge had only 22 layers, whereas the Resnet that won in 2015 had 152 layers. The skip connection is prevalent on all architectures post-2015. We see that it's part of a transformer architecture and also newer models like Mamba. There's another way to implement the skip connection, and that is to concatenate the feature maps. This is something that we see in the Densenet paper and in also other architectures. This is a way in which we preserve the feature maps at the cost of using more memory than in the Resnet's element-wise addition approach. We see that this trick is also implemented in the unit architecture that we have seen before. This is something that allows the model to combine features from the encoder and the decoder path when we're generating segmentation images. We'll explore this in a lot of detail in the practical part. So, to wrap up this video, we saw that the vanishing gradient is a numerical problem, and it comes from the fact that computers have limited precision to represent small numbers. We saw that skip connections serve as checkpoints for what the model has learned, and they give us a chance to preserve information that would have been destroyed due to numerical underflow. We saw that there are 2 types of skip connections. We use either element-wise addition or concatenation. Both of these operations are quite straightforward to implement in PyTorch. They just require us to do 1 or 2 lines of code.